So we need to prove one lemma. Well, this is depth from the last lecture, and this time I remember by heart, but just to be precise and to formulate precisely what we formulated last time, I still use some external memory. Okay, so again, we have a non-negative function, lemma, a non-negative function with compact support on our locally compact group G, and also we have another function rho, also in this class, so that the closed support of F is inside the set where rho is equal to 1. Well, so we have that, and I remind you that such a rho always exists by the Urison lemma, so we can even find many such functions rho. So then for every positive epsilon there exists a neighborhood U of unity. I'll remind you that the collection of neighborhoods of unity was denoted by script U, such that we have the following inequality. Well, and for this rho, it is also assumed that it is between 0 and 1. Okay, so when x and y do not differ much from each other, their, so to say, difference, or in this order, is of size u, then we have the following inequality, and I remind you that this rho was of technical nature, and if you forget about this rho, well, in principle, this is automatic because rho is between 0 and 1. And here we can simply erase rho, and there will be, okay. If we consider this inequality, we see in particular that all this implies that this difference is dominated by epsilon in whatever order, because x and y have the same rights here, so we can interchange them. So in this form, this is merely something like uniform continuity, and mostly, of course, we will use this uniform continuity many times, but mostly in this form, and here we invoke rho for some needs of the proof that I presented last time. So let's prove this in this formulation. with rho. Now, so in the proof there is nothing particularly interesting. It is fairly standard. So take the interior of this set. So it contains the support of K, and for every and let K be the closed support of F. This is a closed compact set. So for every A in K, there is a neighborhood of unity. Some open set. So this is a neighborhood of A. Such that so this is simply the continuity of F. Well, okay, we find such a neighborhood for each A in K, and then we use the fact that this map is continuous from G cross G into G, surely. And since it is continuous, I use the continuity of this map at only one point, at the couple of unit elements, and so there exists a neighborhood of unity such that UA is included in this neighborhood VA. So we find a neighborhood of unity such that we have this. Of course, this is the neighborhood of A. So, okay. And next, we take the collection of such open sets, and this is a covering of K. So I remind you that A runs through K. So this is a covering, and since everything is compact, we can find a finite subcovering. So there is finite set A, so that the union of small a in capital A covers K. Okay. Now, what we do, we simply intersect all these open sets. And this is again a neighborhood of unity because the intersection is finite. And next we do what I explained already last time. Take U equal to U prime intersected with U prime to the power minus 1. This is to make it symmetric, well, to make these two conditions equivalent. Well, now take x, y, so that x to the power minus 1 y is in U. So we require this condition, and this is the same now that this condition, so we may require every of them. They're equivalent right now. Suppose that f of x is strictly positive, because otherwise there is nothing to prove here. Yes? If f of x is 0, there is nothing to prove. Then this x is in K for sure. And then there exists A, so that x is in A UA. Okay? Well, and what's about y? What's about y? And y, it is x, x to the power minus 1 y, and so this is A UA U. Yes, because so x is in K, and this is a covering A in our A capital. So right now I consider only A in capital. So this is a covering, so we can find one, and then if x is here, then y is here, well, and U is what's about U? So it is it was the intersection of all these UAs. So anyhow, from all these inclusions, it follows that both x and y are in VA. And here on VA we have this inequality, but we also have to take rho into account. So what do we have? We have f of x is dominated by f of x plus epsilon, f of a plus epsilon over 2. So we use this with b equal to x, and then we use the same with b equal to y. So this is less than or equal to f of y plus epsilon. And it is clear that at this point y, our function g is equal to, our function rho is equal to 1, because you see, okay, we took this interior and everything happens inside W. So this, well, I forgot to say that we may take this VA in W, because, okay, clear. So everything happens inside W, and on W our function rho is equal to 1. So this is simply equal to f of y plus epsilon rho y, and so on.
Why do you need epsilon over 2?
Because I use this twice. First I replace x by a, and then I replace a by y. So of course, this doesn't matter. Now, so this is simply absolute uniform continuity, slightly refined, Well, the proof is somehow standard when you take some neighborhood of unity and you shift it by elements of our compact set, and then you take a finite covering. But there are some complications because of this function rho. You should take it into account. Okay.
Well, isn't it like you could replace the lesser equal in the last?
Well, just equal. Well,
could you say that?
Yes, maybe, but it is easier to use this in this form when we proved something about existence of Hauer measure, then it was more appropriate to have this form than just equality. Yes, sure. Now, so finally we have proved the existence and the near uniqueness of a Hauer measure, a left invariant Hauer measure. Near uniqueness means that every two left invariant Hauer measures are proportional with some positive constant. Everything was established yesterday and today. Now what's about this multiplicative constant? There are some standard ways to choose it. For example, through normalizations. If G is compact, then the function identically equal to 0 is, of course, among our test functions. And so we have this. So then our left invariant Hauer measure is finite. And it is natural to normalize it so that it becomes probability measure. So we assume normally it is assumed that this measure is equal to 1. So this is the first case. And the second standard case is when G is discrete. G is discrete, the measure of every point is positive because every characteristic function of a singleton is continuous. Continuous and non-zero. So the measure of each point is positive and the measures of all points are equal. So if this group is infinite, then this measure is infinite. So it cannot be made probabilistic, but the normalization is to put that mu of unity is equal to 1 here. Surely there is some contradiction where G is discrete and finite. but well, in that case, it's a matter of convenience what you choose. But normally for discrete groups, you normalize in this way, and for compact groups in that way. And also, of course, there is a right invariant measure. So let G be our group, then there is left invariant mu, and also this is evident, there is a right invariant. Why? Because you can consider what is called the dual group. That is the same group, but where you reverse the order in multiplication. And then everything which was right invariant becomes left invariant. The left invariant measure exists. Then you again consider the dual of the dual. Okay. Well, in fact, these measures need not coincide. They need not coincide. Mu and nu, even up to a constant. They may be different.
Yes.
They may be different.
In compact case,
in compact cases, they coincide. So if G is compact, you may simply consider the following integral. And f is again a test function. Then, of course, you can apply the Fubini theorem, and integrate inside by mu, and then use that this thing is left invariant. And we suppose that both of them are normalized so that to become probability measures. Then, if we use that mu is left invariant, we simply obtain that this is equal to the integral over G of f. The mu, because no. What I am doing? No. In this way. So you use that f is left, mu is left invariant, then x disappears from here because of invariance, and this integral of a constant against this measure gives 1, so you obtain this. And if you reverse the order of integration, you obtain this. So they must coincide in the compact case. But in general, they do not. But they are related to each other somehow. Well, and let us consider a right shift. this time. And let us integrate the right shift of some test function against our left invariant measure mu. Well, this is the following thing, and it is easily observed that this integral is left invariant. When I apply a left shift to, to f, then by invariance, by the left invariance of mu, this thing is left invariant. By the fact that a left invariant measure is essentially unique, we find a constant. Let us denote it by xi of u, so that this is equal to the integral over g of f of x of x. So this is a left invariant Haar measure. Then it is proportional to mu, and then we have the following relation for every test function f. So we obtain such a function. Now, what happens here? Surely this is interesting when this function is non-zero. Because otherwise everything is zero. If it is non-zero, then this guy is non-zero, because we know that any Haar measure gives a non-zero value on each non-zero test function. So this is non-zero, and this is continuous in U by the uniform continuity of f, whatever that means. Here I need to write uniform continuity, but we have proved even two-sided uniform continuity. So if u1 is close to u2, then these functions are uniformly close by the lemma which you proved before this. So this is continuous in U, and the consequence is that xi of u is non-zero everywhere, and continuous in U. So this is a continuous function. And also it is clear that it is a real continuous. Okay, it is clear also that xi of u1 u2 is equal to xi u1 xi u2. So though it doesn't matter, but precisely from the definition we see that this happens. Okay. Well, very often the inverse function, I mean 1 over xc, is called the modular function of g. It turns out that this u, this xi, they in fact relate left and right continuous, left and right invariant Haar measures with each other. Let me show this. Because this is non-zero. This is so take a fixed non-zero test function. Then its integral over the higher measure is non-zero everywhere. This was one of the statements in the theorem which was proved at the very beginning. You remember. And this is also a non-zero test function. So this is non-zero and this is non-zero. So we can express this as the quotient of these two quantities. This quotient is non-zero and is continuous in U. Okay? Well, so this is simple, but requires some concentration. What else? From this it also follows that Xi of E on the unit element is equal to delta of E is equal to 1. Okay? Because it's non-negative, it is non-negative and multiplicative, so it must be equal to 1. Well, consider, so to establish the relationship between a left higher measure and some right higher measure in terms of this function psi or delta, we consider the following two functionals. So again, f is a test function. And we consider first the integral of this sort. And the integral of this sort. So consider these two integrals. And I claim that both functionals are right invariant. Well, for this, if we multiply x from the right by something, then this something after inversion goes to the left, and we just use the left invariance of mu to see that this is right invariant. And for this, we write, apply this to a right shift of f. So we obtain the integral of g c of x f of x y diminutive of x. So this is this one applied to the right shift of f. Then we can do this way. Okay? Simply I multiply it and divide it by this quantity. And after that, we recall what this is. Recall what this is. Well, where it is? Here. Well, so this thing, okay. We integrate over x, then we can erase, we integrate some test function. This is also test function because this has compact support and this is continuous. So the product also has compact support, so this is a test function. So we can erase y here and write xi of y before the integral sign. And this will be the same by this defining relation of xi. So this is the integral over g c of x, f of x, the mu of x. So this is also right invariant. So we have two right invariant functionals, and as we saw, they are proportional. So there is a constant c, so that we have this for every f. And now let's prove that this c is equal to 1. Some explanation. We have already seen that this function is right invariant. So what does this mean? This means that if we supply this mu, the left invariant measure, with this density, then we obtain a right invariant measure. So in a sense, we have established a relationship between right and left invariant measures. But now I'm going to prove that this particular right invariant measure coincides with what can be viewed as a most natural right invariant measure. So if you just replace x by x to the power minus y, then this integral becomes right invariant, and probably this is the most natural right invariant measure given mu. And so they are in fact the same. So that not only that when treated as a density, this gives the right invariant measure, but also this integral coincides precisely with this one. So somehow this function xi is intimately related with the group structure of our group G. Okay. So we have this formula, and of course c here is non-zero as any constant relating to right invariant measures, non-zero positive constant. And now let's write this for the function f tilde of x, which is equal to f of x to the power minus 1. Let's rewrite this. The integral of f tilde of x to the power minus 1 is equal to c, the integral over g of c of x, f tilde of x, d mu of x. And now here we have f tilde of x to the power minus 1. So let me use some technical stuff and to write this in this way. Okay, f tilde of x minus 1 is the same as f of x. So we have the following 1 over c, the integral over g of f of x is equal to the integral over g of f tilde of x and let me here write xc of x to the, well, again, I write here what f tilde is, f to the power minus 1, and here, to retain this minus 1, I write xc in the denominator. So this is an identity transformation. Sure. And after that, we use the defining formula again. Of this, well, not the defining formula, but this formula. This formula, this time applied to this function. Okay? So it will be c times the integral over g of what? Of psi of x, f of x over psi of x, mu of x. And so we recover here the same integral as here, and here it is multiplied by 1 over c, here it is multiplied by c, so c is equal to 1. Okay.
I have some questions for zeta here. What is it?
What is
zeta?
This is this function. This is this function defined in this way, it is multiplicative and non-zero and equal to 1 at 1. So zeta of x is equal to 1 over zeta of x minus to the power minus 1.
I mean, I want to know what is it in the case when g is compact or okay?
It is equal to 1. Sure.
Always.
Always, because every right invariant measure coincides with every left invariant measure. So in the case of a compact group, it's equal to 1 identically. So this is modular function, and when this function is identically equal to 1, the group is called unimodular. So every compact group is unimodular. There are some other unimodular groups, of course, but there are some groups that are not unimodular, and we shall see one such group immediately. So this is a very good question. It may be this function may perfectly be non-trivial. Well, okay. So this is what I'm going to show you is related to the group of matrices. Well, how to say? Of linear and virtual matrices with determinant 1, but this is another, more or less the same thing, but in a different representation. Not quite the same, but more or less. Consider G is a set all matrices of the form x, y, 0, 1, where x is strictly positive and y is arbitrary real number. Well, topologically, this is the right half plane, the open right half plane. If I parameterize it by, if I view this x and y as coordinates, then this is open right half plane, and the set of these matrices forms a group. Well, I don't want to check this, but just count and, well, to see that the product of two matrices of this sort is of the same sort is easy. And, well, here, these elements of these two matrices multiply simply, and that's why this condition is preserved. And to invert such a matrix is also a very easy task. Just write a system of equations and see that it is invertible. It turns out that, but topologically this is a half plane, and so consider the following two measures. E is Borel here. It turns out that this one is left invariant and this one is right invariant. Okay? So our modular function is something, well, either x or 1 over x, I cannot imagine. Delta is, what is delta? Delta is 1 over x probably, yes. Delta is 1 over x. So it is non-trivial here. I don't... This is left invariant. Dy, yes. Sure. It's left, and this is right. Well, to check this is some fairly easy exercise. Just write what this means, and you'll see that through it. So. And of course, this group is non-compact, so that there is no abstraction for these two things being different. They're really different. Another case when left and right is the same is when our group is commutative.
Yes, of course.
Sure. And then this modular function is equal to 1, of course. Well. And now we want to switch, I want to switch to commutative groups. We shall return to non-commutative case for some moment in future, but it seems to me that now it is better to see what happens in the commutative case and then probably return to the non-commutative case having some example as an analogy, so just to watch what is similar and what is non-similar, and in the commutative case everything is fairly well understood. In the non-commutative case, the same theory that exists for commutative groups is available only for compact groups. For non-compact groups, it also exists, but somehow very, very bulky and very complicated. So I'll come back to non-commutative compact groups at some moment, but after we learn what happens for commutative groups. Okay. But before I pass to commutative groups, I need, I don't know, to remind you or probably to inform you about the theory of commutative Banach algebras. I don't know to what extent you know the theory. I think that you know something at least. You know what the Gelfand space is, probably. Gelfand, yes.
Space, you mean the spectrum or
The spectrum, yes, the spectrum.
Okay,
The spectrum, you know what this is. And probably in the case when your algebra is unital, it has a unity. Yes?
Yes.
Yes. In the case when it has unity. So I assume that you know the Gelfand theory in the case when the algebra has a unity. Well, there is also a counterpart of the Gelfand theory for non-unital algebras, and I want to say a few words about that. But first, let me remind you what happens for commutative Banach algebras with unity. Commutative Banach algebra with unity. So let A be a commutative and let M of A be the so-called spectrum or Gelfand space of A. What is that? It is the set of all non-zero multiplicative complex functionals on A. Okay, and I also assume that A has a unity. What?
With unity.
With unity, okay. Okay, with unity, okay. Phi is linear multiplicative at non-zero. Then there are some facts that I assume known. First, all phi in M of A are continuous. And have norm 1. So you are not surprised, yes? Nobody is surprised. Somebody. Do I confer something you didn't hear about? Somebody of you?
Isn't it just obvious?
Sorry?
Isn't it just obvious?
Is it?
Isn't it just obvious from
not quite, because the continuity is not obvious. The continuity is not obvious. The continuity is deduced eventually from the Liouville theorem for complex analysis. So this is not at all obvious. Second, M of A is a W star closed subset of the dual space. W star means in the topology, in the weak topology, induced in A star by A. So since all of them are of norm 1, this is in fact a closed subset of the unit sphere. I mean closed in this weak topology. And since the unit ball of the dual space is always compact in this topology, then this space is compact. Okay? It's compact. Now, so we have some continuous homomorphism pi from A to the space of continuous functions on this spectrum, and pi A of phi, this is simply phi of A. So this is an algebraic homomorphism. Clearly it is linear, it is multiplicative because all functionals we consider are multiplicative. So this is a homomorphism. Now P of A is a separating subalgebra. It separates the points of the complex. Yes, separating subalgebra of. It separates the points because different functionals should differ on some elements, so it separates the points. Now, this is important because if we, in some particular case, know somehow that our algebra is also self-adjoint, this image, then we can use the Stone-Weierstrass theorem and to conclude that this is dense in CMK. Now, the norm of P of A in C of K is the so-called spectral norm. Of A. We always have this inequality. The spectral norm is always dominated by the original norm. This is precisely because all functionals phi have norm 1. Okay? All of them have norm 1. And even the spectral norm of A is equal to the following thing. This is the limit as n tends to infinity of the square of the root of power n, the norm of A to the power n. So I don't know if we shall need this, probably not, but still there is such a relation, and this is also called the spectral radius of A. For certain reasons I don't recall them. Sorry?
What is K here?
What is?
K.
Where?
Like C of K in the...
K, C of K, M of A. M of A. MV. Probably at some point I wanted to replace this by K just to shorten my task, but okay. Well, and basically this is all you should know. If you don't know, if somebody of you don't know, then just take any manual in functional analysis and read this chapter about commutative binary algebras with unity. Okay. Okay. So what is important that here in this setting, when we have a unity in our binary algebra, then this Gelfand space, the spectrum is compact. Now, what happens if there is no unity? Then something similar occurs, but with the only difference that this time the spectrum will be locally compact rather than compact. And this can be done in the following way. So consider an algebra, a binary algebra A without unity, then we can adjoin to unity artificially to this binary algebra. Simply, we can consider the algebra A tilde of pairs A x, where A is an A and x is a complex number. So the unity will be the pair 0, 1. So if we do not have quite strict arguments, then we can view this as A plus x E, where E is this adjoint unity. And from this it is clear how to multiply such guys. If you had some unity, then multiplication will go in the following way. Okay. Here I again switch to this notation. So just there is no way to define multiplication in this algebra except this one. So let's define multiplication in this way. And as to the norm, let's put the norm of this pair simply equal to the norm of A plus the absolute value of x. So that, so to say, we norm this in literal one sense. Then surely we obtain a binary algebra And this time we have a unity in it, and this unity is precisely this thing, 0, 1. And after that we can apply the Gelfand theory to this new algebra. Consider S equal to M of A tilde. This is a compact space. Compact space. On this algebra, there is some distinguished linear multiplicative functional. So consider the functional phi 0 of a x simply equal to x. So this is some distinguished multiplicative linear functional. What's about this functional? Phi 0 of a 0 is equal to 0, so it's equal to 0 on all elements of our initial algebra. Of course, the elements of our initial algebra are identified with space like this. So on everything like this is equal to 0. Okay? So if I take P of A 0, P is a Gelfand transform, and calculate it as a point phi 0, this is equal to 0. So the Gelfand transforms of all functions in my algebra A, in the initial algebra, they vanish at this distinguished point phi 0. So it is natural to exclude this point from our compact space. Well, then what remains becomes locally compact.
So it is one point compactification?
Yes. So this S is 1 point compactification of what remains, sure. because we remove this point, then then we remove this point from a compact space and we obtain something locally compact. After that, let us consider all multiplicative linear functionals that extend, on this algebra A tilde, but which are non-zero somewhere on our algebra, initial algebra. So these are all functions except phi 0. These are all points of S except this phi 0. So we have this transform, and for this transform we have traces of all properties that I recalled. So in fact we can apply this theory also in the case of non-unital algebras, and this will be important for us because we will come across some non-unital algebra very soon on every compact abelian group. One of the difficulties of the non-commutative case is that for non-commutative Banach algebras there is no something similar to Gelfand theory.
I think they call this non-commutative geometry.
Yes, sure there is, but okay. Somehow this is not for presentation like that. This is fairly probably not so difficult, but somehow like what I presented last time. Also not difficult, but not quite pleasant. You know? very many tiny details, and you should remember all of them. And well, during one lecture probably you remember, but then when you come to the second one, then you forget. And okay. So this Gaussian theory can be applied to non-unital algebras, and everything goes very smoothly. The only difference is that the spectrum becomes only locally compact, not compact.